Welcome! In this session, we'll tackle LeetCode problem number 1427, perform string shifts. This problem challenges us to efficiently process a series of shift operations on a string. Get ready to explore the logic, optimize performance, and deepen your problem-solving skills. Let's dive in. The problem is to perform a series of string shift operations on a given string S. The input string has a length n, and the operations are described using an array called shift. Each operation is represented as a pair, direction, amount, where the direction determines the type of shift, and amount specifies how many positions to shift. A direction of 0 means a left shift, which moves the first amount characters of the string to the end. On the other hand, a direction of 1 means a right shift, which moves the last amount characters to the beginning. After applying all the shifts in the array, the task is to return the resulting string. The input string consists of lowercase English letters, and the size of the shift array, as well as the amount values, can be large, making it important to optimize the solution. The output of the function must be the modified string after applying all the shift operations in the given order. Let's look at an example to understand this better. Suppose the input string is s equals abc and the shift array is 0, 1, 1, 2. The expected output is the string cab. We'll see how this result is obtained step by step. First, we apply the left shift operation, 0, 1, which moves the first character of the string to the end, transforming ABC into ca. Then, we apply the right shift operation, 1, 2, which moves the last two characters of the string to the beginning, resulting in the string cab. This demonstrates how consecutive shift operations modify the string in sequence. Another example involves the string s equals abcdfg in the shift array 1, 1, 1, 1, 0, 2, 1, 3. The output here is fgapped. First, applying the right shift 1, 1 moves the last character g to the front, changing the string to gapdef. Repeating the right shift 1, 1 moves the new last character f to the front, resulting in fgapped. Then, a left shift 0, 2 moves the first two characters fg to the end, transforming the string into abcdfg. Finally, the right shift 1, 3 moves the last three characters f to the beginning, yielding the final string fgapped. This illustrates how shifts interact with each other to produce the final result. A third example uses the string s equals xqyw in the shift array 0, 3, 1, 2, 0, 1. The output in this case is ywqx. First, we perform the left shift 0, 3, which moves the first three characters xqy to the end, resulting in the string ywqx. Next, we apply the right shift 1, 2, which moves the last two characters qx to the front, changing the string to qxyw. Finally, the left shift 0, 1 moves the first character q to the end, bringing the string back to ywqx. The sequence of shifts determines the final configuration of the string. The problem also comes with constraints and edge cases that we need to consider. The string s can have up to 10,000 characters, and the shift array can have up to 10,000 operations. Additionally, the amount value in each operation can be very large, up to 10,000. To handle this efficiently, we can use modulo arithmetic to reduce the shift amount. For example, a shift of amount positions is equivalent to amount %len, s, which eliminates redundant rotations. For a single character string, any number of shifts will leave the string unchanged. Similarly, if the shift array is empty, the string remains unmodified. When multiple shifts occur in the same direction, we can combine them into a single operation to simplify the process. For instance, consecutive left shifts like 0, 3, 0, 2 can be combined into 0, 5. This helps optimize the computation and reduces redundancy in the operations. By carefully accounting for these constraints and edge cases, we can design an efficient solution that handles large inputs and ensures correctness. The goal is to use these principles to process the input string and shift array systematically, ultimately returning the desired result after applying all the specified operations. To solve the problem of performing string shifts efficiently, we first consider a brute force approach. The idea here is straightforward. For each shift operation, we directly manipulate the string based on the given direction and amount. For a left shift, we take the first segment of the string and move it to the end, while for a right shift, we take the last segment and move it to the front. This is achieved using string slicing and concatenation. While this method is intuitive and simple to implement, it involves repeatedly slicing the string for each operation. This means that if the string is long or there are many operations, the time complexity grows significantly, making the approach inefficient for large inputs. The brute force approach, as we've seen, has a time complexity of O, n asterisk k, where n is the string length and k is the number of operations. It also uses O, n, space to store intermediate results for each slicing operation. This inefficiency leads us to explore an optimized approach, which focuses on consolidating all shift operations into a single, effective shift. The key realization here is that a shift by the string's length or a multiple of it results in no net change. By reducing the total shift using modulo arithmetic, we can compute an effective shift that combines all operations. Additionally, we recognize that a left shift is equivalent to a right shift by the complement of the string's length. With this understanding, we calculate the net shift by summing up all right shifts and subtracting all left shifts, then reducing the result to fit within the string's length using modulo. Finally, we perform a single slicing operation to apply this effective shift, making the approach both time-efficient and conceptually elegant. To implement the optimized approach, we start by initializing a variable to keep track of the net shift. As we process the input array of shift operations, we adjust this net shift based on the direction and amount specified in each operation. Once all operations are accounted for, we reduce the net shift using modulo to ensure it remains within the bounds of the string's length. With the effective shift calculated, we perform a single slicing operation to rearrange the string. The resulting time complexity is O, n plus k, where n comes from the slicing step and k from iterating through the operations. The space complexity is O, n, for storing the final string, which makes this approach both efficient and practical. By consolidating all operations into one final shift, we eliminate the inefficiencies of repeatedly manipulating the string. Another potential solution involves shifting characters in place using array manipulation. Here, instead of slicing the string, we treat it as an array of characters and reorder it directly. The process begins by converting the string into a list, then calculating the net effective shift using the same method as the optimized approach. To perform the shift in place, we utilize a reverse algorithm. First, we reverse the entire array, then reverse the first segment up to the point dictated by the shift, and finally reverse the remaining segment. This series of reversals effectively rotates the array to achieve the desired result. While this method achieves the same time complexity of O, n plus k, as the optimized slicing approach, it has the added advantage of using only O1 additional space since it modifies the array directly. However, the implementation is more complex and less intuitive, which might make it less appealing for this problem. Considering the different approaches, the optimized slicing method stands out as the best choice due to its balance of simplicity and efficiency. By reducing all operations to one effective shift, we avoid redundant computations and streamline the process. The slicing operation is straightforward to implement, making the solution both elegant and practical. While the in-place shifting approach offers better space efficiency, its added complexity makes it less suitable, especially given the problem's requirements. On the other hand, the brute force method, though simple in concept, is computationally expensive and performs poorly on large inputs. The key takeaway here is the importance of reducing multiple operations into a single effective one, which not only minimizes redundant work but also highlights the power of modulo arithmetic in simplifying the problem. This approach ensures that we can handle larger inputs efficiently without sacrificing readability or maintainability in the code. In this problem, we are tasked with performing a series of left and right shift operations on a given string. Each operation specifies a direction, where 0 indicates a left shift and 1 indicates a right shift, along with the number of positions to shift. The challenge is to determine the final string after all these operations, but we want to do this efficiently without applying each shift individually. To start, we can consolidate all the shifts into a single effective shift. Here's how. First, we recognize that multiple left and right shifts can cancel each other out. For example, a left shift of 3 followed by a right shift of 5 is equivalent to just a right shift of 2, since 5 minus 3 leaves 2. To calculate this, we initialize a net shift variable at 0 and iterate through the list of shifts. For each operation, we adjust the net shift based on the direction, subtracting for left shifts and adding for right shifts. Once we have the total net shift, we can optimize it further by taking it modulo the length of the string. This step ensures that we only consider shifts within the string's bounds, as shifting by the length of the string or any multiple of it results in the same string. If the net shift turns out to be negative, we convert it to a positive equivalent by adding the string length, ensuring the shift direction is appropriately adjusted. Now that we have the effective shift calculated, we can perform the actual string manipulation. Using Python's efficient string slicing, we can achieve this in n time, where n is the length of the string. The idea is to split the string into two parts based on the net shift value. First, we isolate the last net_shift characters of the string using the slice s, net_shift. These characters will wrap around to the beginning of the string after the shift. Then, we take the remaining characters, everything up to but not including the last net_shift positions, using the slice s, net_shift. Finally, we concatenate these two parts, placing the last net_shift characters at the front, followed by the rest of the string. This gives us the final shifted string in an efficient and elegant way. This approach leverages a few key insights to make the solution efficient. First, by reducing redundancy using modular arithmetic, we avoid performing unnecessary shifts. Instead of applying each shift operation individually, we consolidate them into one effective operation, which greatly simplifies the computation. The use of modulo ensures we only consider shifts within the bounds of the string length, making the algorithm robust and efficient. Second, Python string slicing allows us to rearrange the string in n time without manually moving characters one by one. This makes the implementation not only efficient but also clean and concise. Lastly, we account for edge cases to ensure correctness in all scenarios. For instance, if the net shift is 0 after the modulo operation, the string remains unchanged. Similarly, if the string has a length of 1, any number of shifts will result in the same string. By reducing large shift values using modulo, we avoid overflow and unnecessary computations, ensuring the algorithm handles even extreme inputs gracefully. The algorithm relies on two main data structures, the string itself and the list of shifts. The string is manipulated using slicing to achieve the desired shifts efficiently, while the list of shifts is processed linearly to compute the net shift. This simplicity in data structures contributes to the overall efficiency. When analyzing the complexity, the time complexity consists of two main parts: calculating the net shift, which involves iterating through the list of m shifts in m time, and slicing the string, which takes n time for a string of length n. Thus, the overall time complexity is m plus n. For space complexity, the algorithm uses n space for the resulting string, but no additional data structures are required beyond the input itself. Therefore, the space complexity is also n, making the solution both time and space efficient. This implementation for LeetCode problem number 1427, perform string shifts, is efficient and concise. The solution involves consolidating multiple left and right shifts into a single effective shift, reducing redundancy and computational overhead. First, we iterate through the shift array, which contains tuples of the form, direction, amount. For each tuple, we adjust the total_shift variable, subtracting the amount for left shifts, direction 0, and adding it for right shifts, direction 1. This step combines all the shifts into one net value, which represents the overall direction and magnitude of the string rotation. Next, we normalize the total_shift value to ensure it does not exceed the string's length. This is achieved using the modulo operation, total_shift% equals len s, which handles cases where the total shifts exceed the string's length, e.g., rotating a string of length 5 by 10 positions is equivalent to rotating it by 0 positions. We then perform the effective shift based on the normalized total_shift value. If total_shift is positive, it corresponds to a right shift, and we slice the string accordingly, s, total_shift plus s, total_shift. If it's negative, it represents a left shift, and we adjust the value to positive before slicing, s, total_shift plus s, total_shift. If the total_shift is 0, the string remains unchanged, and we return it as is. This method ensures that the solution is efficient, with a time complexity of n, where n is the length of the string, as the slicing operation dominates the computation. The algorithm is also space efficient, requiring only a small amount of additional storage for intermediate calculations. By consolidating shifts and optimizing the slicing process, this implementation effectively handles all edge cases, such as no shifts, excessive rotations, and strings of varying lengths. Here, we start by defining a Java function called stringShift, which takes in a string s and a 2D array shift. The goal of this function is to apply a series of left and right shifts to the string based on the operations specified in the shift array. First, we initialize total shift to 0, which will help us calculate the net effective shift after processing all the operations. Next, we iterate over each operation in the shift array. Each operation contains two values, direction and amount. If the direction is 0, it means we need to perform a left shift, so we subtract the amount from total shift. If the direction is 1, it indicates a right shift, and we add the amount to total shift. After processing all the operations, we normalize total shift by taking its modulo with the length of the string n. This step ensures that we avoid unnecessary full rotations, as a shift by the length of the string or any multiple of it results in no change. With the normalized shift value, we can now determine how to rearrange the string. If total shift is 0, the string remains unchanged and we simply return s. Otherwise, we proceed to check whether the shift is positive or negative to handle the two cases, right shift and left shift. If total shift is greater than 0, it indicates a right shift. In this case, we split the string into two parts, the last total shift characters and the remaining characters at the beginning. We then concatenate these two parts in reverse order to achieve the desired right shift. On the other hand, if total shift is negative, it represents a left shift. To handle this, we take the absolute value of total shift to get the number of positions to shift. Similar to the right shift, we split the string into two parts, this time, the first total shift characters and the remaining characters. We then concatenate these parts, placing the latter part first, to complete the left shift. Finally, the modified string is returned as the result. This implementation ensures that the string is shifted correctly and efficiently, regardless of the number or direction of shifts specified in the input. Here, we start with the string ABCDE and a list of shifts, where each shift is represented as direction, amount. The first step is to initialize a variable called total_shift to 0. This variable will accumulate the net effect of all shifts. Next, we process each shift in the list. The first shift, 1, 1, indicates a right shift by 1. Since the direction is 1, we add the amount to total_shift, resulting in total_shift becoming 1. For the second shift, 0, 2, the direction is 0, meaning a left shift by 2. Here, we subtract the amount from total_shift, bringing it to -1. After processing all shifts, we normalize total_shift by taking it modulo the length of the string. This ensures the shift value stays within the bounds of the string length. In this case, -1 modulo 5 gives us 4, meaning the net effect is equivalent to a right shift by 4. Next, we perform the actual shift based on the normalized total_shift value. Since total_shift is 4 and greater than 0, it indicates a right shift. To achieve this, we take the last 4 characters of the string, which are BCDE, and the remaining characters, from the front. Concatenating these two parts gives us the result BCDEA. For the second example, we have the string ABCDF and shifts 0, 3, and 1, 3. Again, we initialize total_shift to 0. This setup ensures we start fresh for each example. We now process the shifts for the second example. The first shift, 0, 3, indicates a left shift by 3. Since the direction is 0, we subtract the amount from total_shift, making it -3. The second shift, 1, 3, is a right shift by 3. Here, we add the amount to total_shift, bringing it back to 0. After processing both shifts, we normalize total_shift. Taking 0 modulo the length of the string, which is 6, gives us a total_shift of 0. This means there is no effective shift, as the net effect of all shifts cancels out. Therefore, the original string ABCDEF remains unchanged, and this is the output. In the third example, the string is XYZ, and the shifts are 0, 5, and 1, 8. As always, we initialize total_shift to 0. For the first shift, 0, 5, which is a left shift by 5, we subtract the amount from total_shift, resulting in -5. The second shift, 1, 8, is a right shift by 8, so we add the amount to total_shift, bringing it to 3. After processing the shifts, we normalize total_shift by taking 3 modulo the length of the string, which is 3. This results in a total_shift of 0. The normalization step confirms that the net effect of these large shifts is equivalent to no shift at all. Since total_shift is 0, we do not need to perform any shift on the string XYZ. The original string remains unchanged, so the output is simply XYZ. This example highlights how normalization effectively handles large shift values, reducing them to their equivalent within the bounds of the string's length. By applying these steps consistently, we can handle any combination of shifts efficiently and accurately. To analyze the time complexity of this solution, we can break it down into 3 main components. First, calculating the net effective shift involves iterating through the shift list, which contains k elements. For each element, we determine the direction and amount of the shift, and this process takes k time. Then, we normalize the shift by calculating the remainder of total_shift divided by the length of the string, n. This modulo operation is highly efficient and runs in constant time, 1. Finally, performing the effective shift involves slicing the string into 2 parts. For a positive shift, we take s, total_shift in s, total_shift, while for a negative shift, we adjust it to a positive value and slice accordingly. Each slicing operation requires copying up to n elements, making this step n in the worst case. Combining these, the total time complexity is k plus n, where k is the number of shifts and n is the length of the string. Now let's examine the space complexity. The solution primarily uses a single integer variable, total_shift, for all calculations, which requires constant space, 1. However, when we perform the string shift, new substrings are created due to slicing. For example, s, total_shift and s, total_shift, are temporary substrings that are concatenated to form the final result. The total length of these new substrings is equal to the length of the original string, n. As a result, the slicing and concatenation operations together require n additional space. Therefore, the overall space complexity of the solution is n, driven by the need to allocate space for the new string. To put this into perspective, let's compare the optimized approach to a brute force method. In the brute force approach, we would perform each shift operation specified in the shift list individually. Each of these operations involves manipulating the string, which takes n time per operation. With k operations in the list, the total time complexity becomes k*n. By contrast, the optimized approach avoids these redundant operations. It calculates the net effective shift in k time, normalizes it in 1 time, and performs the shift in n time, giving an overall time complexity of k plus n. For space complexity, both approaches require n space to account for the new string creation. However, the optimized approach is mathematically proven to be more efficient, as it significantly reduces computational overhead by leveraging modular arithmetic to consolidate operations. A common challenge with this problem is misunderstanding the effective shift amount. For example, directly applying the given shift value without considering the string's length can lead to redundant computations. To fix this, we use the modulo operation, k equals k mod the length of the string. This ensures the shift stays within bounds, avoiding unnecessary work. Another common mistake is confusing left and right shifts. Remember, a left shift moves characters from the front to the back, while a right shift does the opposite, moving characters from the back to the front. Testing with small examples can help solidify this understanding. Additionally, inefficient string concatenation in loops is something to avoid. Instead of repeatedly appending substrings, which introduces high complexity, use slicing and concatenation in a single operation, such as combining s-k with s up to -k for right shifts. Lastly, don't overlook edge cases. Scenarios like empty strings, k equal to 0, or strings with a length of 1 should be part of your test plan. Adding early return checks can help you handle these gracefully. Another potential pitfall is attempting to modify the string directly, which is not allowed in Python due to string immutability. The solution here is to create a new string with the shifted result and reassign it to the existing variable. From an interview perspective, this problem evaluates your ability to optimize by identifying patterns, like how modulo arithmetic simplifies the shift calculation. A key realization is that left and right shifts are inverses of each other, which allows you to reduce the problem to a single operation. Efficiency is another focus area, as interviewers often expect a solution with O(n) time complexity for larger inputs or multiple operations. When discussing your approach, clearly explain how you use modulo to calculate the effective shift, as it demonstrates your strategic thinking. Finally, be prepared for follow-up questions, such as handling streaming input or working with limited memory. These scenarios test your adaptability and depth of understanding. This problem is part of a broader category of string manipulation challenges, and understanding related problems can deepen your skills. For instance, in LeetCode 796, Rotate String, you determine if one string can be transformed into another through rotations. This directly ties into the concept of shifting. Similarly, LeetCode 189, Rotate Array, applies a comparable logic for rotating arrays. LeetCode 58, Length of Last Word, emphasizes efficient slicing techniques, which are also useful for handling shifts. Lastly, LeetCode 443, String Compression, focuses on optimizing string operations, reinforcing the importance of efficient methods when manipulating strings. Familiarity with these problems can provide additional context and strategies for tackling string-related challenges effectively. When solving this problem, there are several approaches to consider, each with its own trade-offs. The naive method involves applying the shift operation repeatedly, step by step. While straightforward, this approach is inefficient, with a time complexity of O(k) times n, making it unsuitable for larger inputs. A more optimized approach is slicing and concatenation, which achieves the shift in O(n) time by directly constructing the result. However, this method requires additional space to store the new string. For scenarios with limited memory, an in-place simulation may be used. This involves rotating the string in place using reverse operations, though it's more complex to implement and typically less intuitive for strings compared to arrays. Each approach has its merits and drawbacks, so the choice depends on the constraints of the problem and the resources available. Great job! We successfully tackled the perform string shifts problem, focusing on efficient string manipulation and modular arithmetic. Remember, mastering these concepts will help you in many coding scenarios. Thank you for watching, and don't forget to like, subscribe, and share for more engaging content. Keep practicing and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!